8.5 Lesson 2 Partial Fractions. Objectives. 1. You will know that a rational expression may be decomposed as a sum of partial fractions, and that the form of the partial fraction decomposition is determined by how the denominator of the rational expression is factored. And I will give you some resources that you can refer to for different forms of partial fraction decompositions that you can have. But today we're going to focus on particular forms of partial fraction decompositions. You will be able to find the partial fraction decomposition for a rational expression whose denominator factors as a product of distinct linear factors, as we saw yesterday, and b, as a product in which a linear factor is repeated. So we'll take a look at an example for that. And just like yesterday, you'll be able to use partial fraction decomposition with linear factors to integrate rational functions. Vocabulary: partial fraction decomposition, rational function, and then as we saw yesterday, there's something called the basic equation, in which we have some constants and we solve for those. And then at the end result of partial fraction decomposition is that you're able to rewrite a rational function or a rational expression as a sum of partial fractions. Here's our first example for today. We have number 14. We have the indefinite integral of x cubed minus x plus 3 divided by x squared plus x minus 2. And we're integrating with respect to x. If you look at the integrand, you see that it is a rational expression. Furthermore, the degree of the numerator is greater than or equal to the degree of the denominator, and that makes this an improper rational expression. So we can do partial fraction decomposition, but you have to begin by actually dividing the numerator by the denominator and to rewrite the integrand, and then you can do partial fraction decomposition. So we have to begin with polynomial long division, where our dividend is the numerator, our divisor is the denominator, and after we divide, we will have a quotient and a remainder, and we can rewrite the integrand as quotient plus remainder over divisor. And it is this part that we will apply partial fraction decomposition to, and the other part we should be able to integrate using other methods. And here is an example with integers to demonstrate the same concept that we're about to see with polynomial long division. So here you have the dividend, here you have the divisor, the quotient that we have is 106 and the remainder is 3, and you can write dividend over divisor as quotient plus remainder over divisor. So we'd like to do that with the integrand now. So we're going to go ahead and replace the dividend with our numerator, which is x cubed. And I'd like to have a placeholder. I'm missing a second degree term, so I'll write 0x squared minus x plus 3. And our divisor is the denominator, which is x squared plus x minus 2. So now we're going to go ahead and take a look at how to proceed. This is called the polynomial long division algorithm. And it is similar to the division algorithm that you have with integers, which is of course shown here on the left. But what did you do when you were dividing integers? You looked at 4 and you asked, how many times does 4 go into 4? It went into 4 once. You wrote 1 there. And then you did 1 times 4 is 4. Wrote the 4 here. Subtracted, brought down the 2. You'll see that what we do with polynomial long division is similar. So here's what we do. You look at the x cubed from the dividend and you divide that by x squared from the divisor. So x cubed divided by x squared is x. And you're going to write that here in place of the quotient. And just like you multiplied 1 times 4, you're going to multiply x to each term of the divisor. And when you do that, you get x times x squared is x cubed, x times x is x squared, and x times negative 2 is negative 2x. And then you're going to subtract, just like we did with polynomial integer division. So we're going to do the same thing. So when you subtract like terms. So you have negative x minus negative 2x, or negative x plus 2x, which is negative x. And then you have 0x squared minus x squared, which is negative x squared. And then you have x cubed minus x cubed, which is 0. And just like you did with integer division, you're going to bring down the 3 here. And now you're going to continue similar to how you would have done with integer division, but now you just look at negative x squared, and you will divide that by x squared, which gives you negative 1. And you're going to write that here, minus 1. And then you will multiply that negative 1 to each term of the divisor, and you're going to have negative x squared minus x plus 2. And then subtract, and 3 minus 2 is 1, and when you subtract the other terms you get 0. So this is what we have, and now we're going to rewrite our integrand in the format that I had said earlier. I realized that I just made a mistake a little bit earlier, and here's the mistake that I made. If you're doing negative x minus negative 2x, it's negative x plus 2x, which is positive x. And so when you subtract, what do you have? You have x minus negative x, which is x plus x, which will give you 2x. So you actually have a 2x plus 1 for the remainder rather than just 1. So with that corrected, I am now able to rewrite my integrand as follows. My integrand is dividend over divisor, which is x cubed minus x plus 3 divided by x squared plus x minus 2. And having done the polynomial long division, I know what my quotient is. My quotient is x minus 1, and I'm able to replace the remainder with 2x plus 1. The remainder is 2x plus 1, and the divisor is x squared plus x minus 2. So now I'm able to rewrite the integrand as you see here. So the integrand is rewritten after the polynomial long division as x minus 1 plus 2x plus 1 over x squared plus x minus 2, and we're integrating with respect to x. And of course, you can write this as x minus 1 dx, the indefinite integral of x minus 1 with respect to x, plus the indefinite integral of 2x plus 1 over x squared plus x minus 2 with respect to x. And the reason why I want to do that is because this is something that I can do very easily, and this is something that we can do using partial fraction decomposition. So for the first definite integral, it's easy to find an antiderivative of x minus 1. And then we will have the definite integral of 2x plus 1 over x squared plus x minus 2. And we can figure this out by using partial fraction decomposition. So like we learned yesterday, the first step in doing partial fraction decomposition is to factor the denominator. So we begin with the integrand, we like to write that as a sum of partial fractions. So our first step is to factor the denominator. So we can factor the denominator as follows. We can have x, and then we're going to have 2 and -1. If you check by using FOIL, you'll see that you get x squared plus x minus 2. And because of that, we know what form our partial fraction decomposition will have. Our partial fraction decomposition will have the form that I'm about to write here. Our denominator factored as a product of two distinct linear factors. They're different from each other. So for each linear factor, we will have one partial fraction, and the numerators are constants that we have to solve for. The next step is to multiply both sides of this equation by the LCD, the least common denominator. And the LCD is simply how the denominator factored. It's x plus 2 times x minus 1. On the left side of the equation, the LCD will cancel with the denominator, giving us 2x plus 1. On the right side of the equation, you will distribute the LCD to each partial fraction. In the first one, the denominator will cancel the factor x plus 2, leaving you with a times x minus 1. In the second one, the denominator will cancel the factor x minus 1, leaving you with b times x plus 2. This is what we call the basic equation, and now we're going to solve it by treating it as an identity and working backwards to find the values of a and b that would make it an identity, because that's what we want. We just want an equivalent expression for what we had originally. So let's solve the basic equation by choosing values of x that would allow us to find values for a and b. We can let x be equal to 1, and if x is equal to 1, what do we have? 1 minus 1 is 0, so you have a times 0 is 0. And if you substitute 1 for x here, 1 plus 2 is 3, so you have 3 times b. And if you substitute 1 for x here, 2 times 1 is 2, plus 1 is 3. So you have 3 is equal to 3b, so b is equal to 1. So we know b, but we still have to find a. So to find a, we can let x be equal to -2, because that would make this term 0, and we can solve for a. So let x be equal to -2. So 2 times -2 is -4, plus 1 is -3, and then -2 minus 1 is -3. So we have a is equal to 1. So we know a and we know b, both are 1. With that, we're able to replace a and b here with 1 and 1. And that would allow us to rewrite the integrand here as 1 over x plus 2 plus 1 over x minus 1. And I'll go ahead and do that before I erase anything. So I'm able to rewrite the integrand as 1 over x plus 2 plus 1 over x minus 1. And now I can erase the work that I did to get there. And of course, don't forget what you had in addition to that. And now we're going to use the log rule for integration to integrate. And remember the log rule of integration. Sometimes you need to do a u-Substitution, and sometimes you might be able to do it mentally. In our particular problem here, you could let u be equal to x plus 2, and you can use a different variable other than u, or you can just keep it straight in your head and say let u be equal to x minus 1 for the second partial fraction. But in either case, du will be equal to dx, and this is a pretty simple substitution that you can carry out mentally, or you can write it on paper if you prefer. But when you apply that, this is what you'll have for your antiderivative. For the first partial fraction, you'll have natural log of the absolute value of x plus 2. And then for the second partial fraction, you'll have natural log of the absolute value of x minus 1 plus a constant of integration. And this is it. That's the answer. Sometimes you will see, for example, on the AP exam, that you might get this answer, but perhaps the answer is written in a different form. For example, here you have a sum of two logarithms with the same base. So you can use something called the product property of logarithms to rewrite that as follows. You can write that as the natural log of the absolute value of the product of these two arguments. So you can write that as x plus 2 times x minus 1. And if you multiply it out, you get x squared plus x minus 2 plus c. And there's the final answer for our first example. Here's our second example, number 20. We have the indefinite integral of 4x squared over x cubed plus x squared minus x minus 1 dx. And again, you look at the integrand, and it's a proper rational expression, and we'd like to go ahead and try partial fraction decomposition to rewrite the integrand and see if that helps us to integrate. So step one in the process of doing partial fraction decomposition is to factor the denominator, and we'll go ahead and do that. You look at this problem and you say, yesterday math was such an easy game to play. So now let's go ahead and do that, and we're going to go ahead and, when you look at this denominator here, what you see are 4 terms. And when you have 4 terms and you'd like to factor, you can try factoring by grouping. So we're going to group the first 2 terms, and we're going to group the last 2 terms. And you can factor out the greatest common factor of x squared from the first group, and we're left with x plus 1. And you can factor out the greatest common factor of negative 1 from the second group, and you're left with x plus 1. And the reason why I factored out negative 1 from the second group is because I wanted to be left with a common factor to x plus 1. Because now what you have is a difference of 2 terms, or you can write this as plus negative if you prefer. You have a sum of 2 terms, and the 2 terms have a common factor of x plus 1. So you can factor out x plus 1 from each term. From the first term, you'd be left with x squared, and from the second term, you'd be left with negative 1. There is that factor of negative 1. So you're left with negative 1 there. And of course, x squared plus 1 is a difference of 2 squares, and you can factor that as x plus 1 times x minus 1. So now what you see is that the denominator factors as a product of linear factors, but you have a repeating linear factor. The linear factor that repeats is, of course, x plus 1. You have that twice. So you have x plus 1 times x plus 1, or x plus 1 squared. So the question is, when you have this type of denominator, what form should the partial fraction decomposition have? And of course, this is what we wanted to look at for objective 2. You will be able to find the partial fraction decomposition for a rational expression whose denominator factors as a product in which a linear factor is repeated. So what is the form of the partial fraction decomposition if you have the denominator factor as a product in which a linear factor is repeated? So we will go ahead and make some room on our screen, just remembering how our denominator factored is sufficient. And now we're going to rewrite the integrand by using partial fraction decomposition. And the first step is to write the form of the partial fraction decomposition. So after you factor the denominator, which we would call the first step, the second step, if you want to call it that, would be to write the form of the partial fraction decomposition. And because of how the denominator factored, you will actually have not 2 partial fractions, but 3 partial fractions. And you will have the denominators of each partial fraction as follows. The denominator of the first partial fraction will be just x minus 1. The denominator of the second partial fraction will be just x plus 1. And the denominator of the third partial fraction will be x plus 1 to the second. And the numerator of each partial fraction will be just constants a, b, and c. And like we've seen before, we want the two sides of this equation to be identical expressions. In other words, we want to find the values of a, b, and c that would make this equation an identity. And the way we will do that is by assuming that we have an identity and working backwards to find the values of a, b, and c. Now we will multiply both sides of our equation by the LCD. And the LCD is just the denominator of the rational expression. And you can write it in factored form, x minus 1 times x plus 1 squared. And you're going to multiply both sides of the equation by the LCD. So when you multiply it on the left side, it will cancel with the denominator, leaving you with 4x squared. When you multiply it on the right side, you will distribute it to each partial fraction. When you distribute it to the first partial fraction, it will cancel with the x minus 1 in the denominator, leaving you with a times x plus 1 squared. When you distribute it to the second partial fraction, it will cancel with the x plus 1 in the denominator, leaving you with b times x minus 1 and the other factor of x plus 1. And when you multiply with the third partial fraction, it will cancel with the x plus 1 squared in the denominator, leaving you with c times x minus 1. Now that we have the basic equation, we need to solve for a, b, and c by choosing some convenient values of x. Now we will solve for the constants a, b, and c by choosing some convenient values for x. So for example, if you choose x to be negative 1, then negative 1 plus 1 is 0. Negative 1 plus 1 is 0. These two terms will be 0, and you'd be able to solve for c. So you can let x be negative 1. Negative 1 squared is 1, so 4 times 1 is 4. So we'll have 4 is equal to, and the reason why we let x be equal to negative 1 is so that these two terms will be 0. So now we just have negative 1 minus 1 is negative 2, so you get negative 2 times c. So you can solve for c by dividing both sides of this equation by negative 2, and you get c is negative 2. So we know c, and now we can choose x to be a different value. We can choose x to be positive 1. If you choose x to be positive 1, 1 minus 1 is 0. b times 0 times whatever number you have here is 0. 1 minus 1 is 0. c times 0 is 0. And you'd be able to solve for a. So now we substitute 1 for x, and we have 4 times 1 squared, which is 4. That's equal to a times 1 plus 1 is 2, so you have 2 squared. So you have 4 is equal to 2 squared is 4. So you have 4a. Divide both sides of the equation by 4, you get a is equal to 1. So now we know c and we know a. We've already let x be equal to negative 1. That helped us to find c. We've already let x be equal to positive 1, and that helped us to find a. There's no other value of x that's convenient to help us find b. So what do? You're going to go ahead and substitute what you just found for a and c into the basic equation and choose a different value of x that you haven't used yet and solve for b. So we will have 4x squared is equal to 1 times x plus 1 squared plus b times x minus 1 times x plus 1 plus c is negative 2. So you have negative 2 times x minus 1. So now we have this basic equation with known values for a and c, 1 and negative 2, and we're ready to solve for b by choosing a value of x that we haven't used yet. We've already used 1 and negative 1. An easy value that we haven't used yet that we can use is let x be equal to 0. If you let x be equal to 0, you have 4 times 0, which is 0. And now we can solve for b by just substituting 0 for x wherever we see x on the right side of the basic equation. So you have 0 plus 1 is 1, 1 squared is 1, plus b times 0 minus 1 is negative 1, 0 plus 1 is positive 1, and then plus negative 2 times 0 minus 1 is negative 1. So you have 0 is equal to 1 plus negative 1 times b plus positive 2. 0 is equal to 2 plus 1 is 3 minus b. So b is equal to 3. So to summarize, we found earlier that a was equal to 1. We just found now that b is equal to 3, and we found earlier that c was equal to negative 2. And now that you know a, b, and c, you have completed your partial fraction decomposition, and the integrand can now be rewritten as a is 1, so we can write 1 over x minus 1. B is 3, so we can write 3 over x plus 1. And c is negative 2, so we can write plus negative 2 over, or minus 2 over x plus 1 squared. And that is the form of the partial fraction decomposition that we have. So the partial fraction decomposition that we did will allow us to rewrite the integrand as a sum of 3 partial fractions. And as we've seen in our prior examples, we can use the log rule for integration to find the antiderivative. Or you may have to do something else, as we will see for one of the partial fractions in this example. But the first 2 partial fractions, you can use the log rule for integration. And you will get, for the first partial fraction, when you apply the log rule for integration, natural log of the absolute value of x minus 1. For the second partial fraction, there is a constant factor of 3 in the numerator that you can factor out. And then you will have natural log of the absolute value of x plus 1. And for the third partial fraction, you can do it as follows. You won't be using the log rule for integration. So you'll have minus 2 times the indefinite integral of. You can write x plus 1 squared in the denominator as x plus 1 to the negative 2 power in the numerator. And then you're going to use the power rule for integration, where you will add 1 to the exponent and divide by the new exponent. So we're going to have natural log of the absolute value of x minus 1 plus 3 times the natural log of the absolute value of x plus 1. And then add 1 to negative 2. Negative 2 plus 1 is negative 1. and divide by negative 1, which is the same as multiplying by negative 1. So I get plus 2 times x plus 1 to the negative 1 power, or x plus 1 to the first power written in the denominator, plus constant of integration c. And there it is. We're done with the problem. And this particular problem was done using partial fraction decomposition. Our last example is number 42. Use substitution to find the integral. So we will have to do partial fraction decomposition. But if you'd like, you can begin by using a u-substitution. So you can let u, or if you would like to do the factoring first, you can do that as well. But the main thing is this. In the denominator, if you notice, you have two terms with a common factor of cosine x. So you can factor out cosine x from each term. And if you factor out cosine x from the first term, you're left with 1. And if you factor out cosine x from the second term, you're left with cosine x. So the denominator factors as a product of two factors. And if we use substitution, look at what the problem becomes. We're going to use the substitution, let u be equal to cosine x, and we have cosine x in the denominator. Then the differential of u would be negative sine x dx. And that's nice because we have sine x dx. But we need to multiply both sides of this equation by negative 1. So we have negative 1 du is equal to sine x dx. So now we are able to change variables using our u substitution. And we're going to have negative 1 times du. And in the denominator, we're going to have u for cosine x. So we have u times 1 plus u. And you can see that our integrand is already already has a denominator that's been factored. If you were to multiply the u to the 1 plus u, you'll have the denominator be u plus u squared. And the integrand is in fact a rational expression. But the denominator has already been factored, so we can proceed to the form of the partial fraction decomposition. One thing that you could do is factor out the negative 1 from the numerator. You could do that. You don't have to. That is optional. But you could do that, and if you do it, then this is what you would have. And we can write the partial fraction decomposition for the integrand, and then proceed to integrate using partial fraction decomposition. So the form of the partial fraction decomposition in this problem is as follows. So you're going to just work with what we have here, and you write 1 over u times 1 plus u. The form of the partial fraction decomposition is you will have two partial fractions. The denominator of the first one is u. The denominator of the second one is 1 plus u. And the numerators are constants that we need to find. And following the same logic and procedure that we've discussed in prior examples, we're going to multiply both sides of this equation by the LCD. And on the left side we will have 1, and on the right side we will have a times 1 plus u plus b times u. And now we will assume that we have an identity for this basic equation and work backwards to find the values of a and b that would make this basic equation an identity. So we can let u be equal to 0. When u is equal to 0, we will have 1 is equal to a. That's it. So we know a is 1. And if we let u be equal to negative 1, then we will have 1 is equal to negative b, which means b is equal to negative 1. So we are now able to replace a and b in the form of the partial fraction decomposition with 1 and -1. So now we're able to replace the integrand with 1 over u minus 1 over 1 plus u. And if you like, you can now multiply by the -1 that was previously outside. And if you do that, then what we will have is, for the integrand, we will have 1 over 1 plus u minus 1 over u. And now we're able to integrate using the log rule for integration. And we will have, using the log rule for integration, natural log of the absolute value of 1 plus u minus the natural log of the absolute value of u plus a constant of integration. If you are doing this problem on the AP exam, you may have the antiderivative expressed in a different but equivalent form, for example, using properties of logarithms. So you have a difference of two logarithms with the same base. There's something called the quotient property, and you can write that as the natural log of 1 plus u divided by u, all in absolute value. And of course, in this particular problem, we did a u-substitution. So we want to go back to our original variable of integration, which is x. So what is u? U is cosine x. So I write natural log of the absolute value of 1 plus cosine x over cosine x plus c. And again, if it were like a multiple choice problem on the AP exam, then you might have the answer in a different form. For example, 1 divided by cosine is secant, so you would have natural log of the absolute value of secant x, and cosine divided by cosine is 1. So secant x plus 1, natural log of the absolute value of secant x plus 1 plus c. And that is how we use substitution to find the integral for number 42. Today we looked at examples in which the partial fraction decomposition took different forms. The form of the partial fraction decomposition was determined by how our denominator factored. And in one example, we had a product in which a linear factor was repeated when the denominator was factored. And in the other examples, we had a product of distinct linear factors. And depending on how the denominator factors, you will have different forms of the partial fraction decomposition. And then we were able to use partial fraction decomposition with linear factors to integrate rational functions.